All right, we've made it to part C of this Regents exam. Part C are the last few questions, 66 through 85. And these are the major short answers. In other words, the ones that require a little bit more explanation. But I want to warn you, when you're writing explanations for questions, keep it simple. Okay, you don't need to overcomplicate things. You don't need to write really long paragraphs. It gives you lines to write on in the answer book, and really that's the extent of how much you should be writing. Nothing more than a sentence. So keep it simple and use your reference table as much as you can, but don't overcomplicate the questions. So let's start with question number 66. There are a few pictures here of planets, Mercury, Venus, Jupiter, and Saturn, and all of them have an Earth in them to compare their sizes. It gives you a little bit of information about their structure, their inner core, and so on. Question number 66 actually has very little to do with the diagram. It's asking how many times larger is Jupiter's diameter than Earth's diameter. Okay, so Earth and Jupiter are being compared here, and we just have to use our reference table. Specifically, it's going to be page 15 of the reference table, the chart that has all of the solar system information. So I'm going to go to the solar system chart on page 15. Here it is. And again, we're looking at the equatorial diameter. So let me just circle that. Here's the equatorial diameter of Jupiter, which is the really large planet of 142,984 kilometers, and Earth, which is 12,756. So I'm just going to take those two numbers and I'm going to divide them to figure out how much bigger Jupiter is than Earth. So just a quick calculation here. 142,984 divided by Earth's diameter, which I already forgot, pull it back up again, 12,756. And that gives us our answer of 11.2 times greater. So you can write 11.2, you could write 11. Either way, the answer is going to be 11.2 times greater than Earth's diameter. Okay? Number 67. Explain why Jupiter appears brighter in the night sky than Mercury, despite Jupiter's greater distance from Earth. So the question explains that Jupiter is much farther away, but it's much brighter. And there are multiple answers you could say for this. One answer is that it's just bigger. Jupiter is bigger, and therefore reflects more light. And so that would be a simple, basic answer that I think everybody could kind of think of, that Mercury is really, really tiny, and therefore doesn't reflect very much light. Also, because Jupiter is made from gas, it just reflects light naturally. And because of those two things, basically, Jupiter appears brighter in the sky. Now, there are other possible answers that the Regents would accept, and you can think about logical answers that might go along with that, but that's basically the idea. Okay, question number 68. Identify 2 terrestrial planets shown in the models. Explain why they are considered terrestrial planets. So, in this diagram, remember there are 4 planets shown. Technically, there are 5 because you could include Earth in this. Mercury and Venus, Jupiter and Saturn. Which ones are terrestrial? Well, remember, terrestrial means they have a rocky outer crust. Okay, so basically, Jupiter and Saturn are gas giants. They're made from gas on their outsides. And Mercury and Venus and Earth are all terrestrial planets. So you could pick any one of those 3 planets. I'm just going to say Mercury. And again, you could pick Venus or you could pick Earth because those are all shown in the diagram. And you would say because it has a rocky crust, okay, or a solid crust. The other 2, Jupiter and Saturn, have a gas surface, okay? So that's the basic message behind number 68. You could also say because it's more dense, okay, that's another possible answer, but essentially that's the idea behind question number 68. All right, questions 69 through 72 are based upon this diagram of a river flowing downhill from the mountains all the way down to a lake, and it's depositing its sediment into the lake. Now, question number 69 is a specific question asking about the feature, the landscape feature, or the depositional feature that is called C. And that's just one that you're going to have to recall. Hopefully remember that at the end of a river where it deposits into a lake or into the ocean, that's called the delta. So that's just one you're just going to need to know and remember what a delta kind of looks like. It's fanning out. That's where a lot of deposition takes place because that's where the river slows down as it reaches that still body of water. Number 70. Number 70 requires drawing a cross-sectional view of the general shape of the stream bottom from X to Y. And I want you to notice X and Y. X is on the outside of the curve. Okay, and I'm just going to write outside of the curve. And Y is on the inside of the curve. And so that's worth noting because those two sides are going to have different velocities, and therefore they're going to be different depths. It's not in a straight part of the stream, it's right on the meander, right on the curve. So we're going to need to draw what it looks like from a profile view or a cross-sectional view. So I'm going to pull up that picture from your answer booklet. All right, so here's the stream surface from X to Y, and recall that X is the outside of the curve, and on the outside of the curve, it's a stream going faster. So it's going to be faster over here, and it's going to be slower on the inside of the curve on the Y side. So I need to make it deeper on the faster side of the curve, and so it's going to curve down quite a bit at X, and then it's going to come up shallower on the Y side. And so obviously there's a definite difference between the X and the Y side of the stream just because it's going a little bit faster on the X side and a lot slower on the Y side. So there's a lot of erosion happening over here, and you don't need to label this. All you had to do is draw that blue line I just drew. And there's a lot of deposition happening over on this side, so it's a little bit shallower. So just to recall all of that information regarding streams, remember on a curved stream, there's a definite difference in the profile of the stream. So that's number 70. Okay, question number 71. Describe how the size and the shape of sediments will most likely change as they are transported downstream. What are the sediments going to look like by the time they get to the end? And that's just one where you got to remember that in a stream, there's a lot of abrasion taking place, right? And abrasion is that process by which sediments become rounded and basically a lot smaller. So you need to say something about both of those things. You need to say something about the size and the shape. So they'll become smaller as they wear off their edges, pieces will break off, and the sediment will become much smaller, and the shape of them will become much rounder. Okay, it'll become more rounded. As those abrade and rub up against each other, the sharp edges will break off. So that's just one where you have to know essentially what abrasion is all about. I'll write abrasion here just because I think abrasion is a worthwhile term to know as well. Okay, so that's question number 71. Number 72 is a reference table question. It's asking about stream velocity, and the stream velocity chart can be found on your reference table page 6. I'm going to go to that in a second, but let's just look at the numbers that we need to know about. The stream is going 100 centimeters per second at location A, and it slows down at B to just 10 centimeters per second. We need to know what's going to stop moving, what's going to be deposited. So we need to kind of look at the reference table page 6 to figure out the answer to that question. So let's take a look. On page 6, we have the stream velocity chart in the top right corner. Let's find 100 centimeters per second to start off with. That's located right here, 100 centimeters per second. So I'm going to go up the line until I get to my graph right there. Now at the moment, you can see off to the right-hand side, pebbles are being transported, as well as anything below pebbles, so sand and silt and clay. But as this stream slows down, so it's going to slow down and it's going to curve down here, and eventually it gets to 5 centimeters per second. So if I follow that up right there, you'll notice if I go across now, the only thing being transported now is sand, silt, and clay. Pebbles are no longer being carried by this stream, and therefore they are deposited as it slows down. So pebbles is the answer to that question. So I'm going to write pebbles for number 72. So that's questions number 69 through 72. All right, questions 73 through 76 are based upon this map of the United States, and you have a couple of locations on here, Riverhead, New York, and Hastings, Nebraska, and you can see where they're located on this map. It also gives you a air temperature reading, average monthly air temperature readings for both locations, and there are slight differences between them. Obviously, you can tell that they both increase temperature in the summertime and decrease in the wintertime. And I'd like you to notice that there is a much higher variability. In other words, the temperature of Nebraska in the summertime average is higher than New York State. It's up here, okay? And in the wintertime, it's actually a little bit colder compared to New York State as well. So there's a slight difference there, a little bit more variation, which is what question number 73 is all about. Question number 73 basically asks, why is there a greater temperature difference between winter and summer in Nebraska? And that is because of its location. It's all about where it is on this map. Riverhead, New York is right next to the Atlantic Ocean. It's right on it. Hastings, Nebraska is right in the middle of the continent. And for that reason, it's got a much greater difference in temperatures throughout the year. Riverhead being next to the ocean is kind of moderated by the temperature of the ocean. And so you basically have to say something about that. Nebraska, Hastings is in the middle of a continent, okay? Or you could say something about how Riverhead is next to the ocean, and it's moderated by that, okay? But you just have to explain the idea that it's really the proximity to the ocean. Okay, and the ocean stays the same temperature, relatively speaking, throughout the entire year, and it kind of keeps it like an even temperature and even climate in that location along that big body of water. Okay, so that's number 73. 74, why is the angle of insolation in both locations the same? And the answer to that question is all about latitude. Angle of insolation is the angle of the sun above the ground. So if I were to draw kind of a diagram, here's the sun, and here's the ground, and it's shining down on both locations. And this angle to the sun is the same in both of them. Why? Because if you look at the map, Riverhead, New York, and Hastings, Nebraska, are basically right on the same latitude line, okay? And because of that, we have a very similar angle of insolation. And so I'm just going to write for that answer that it is the same latitude. Simple as that. Okay, so that's number 74. Let's take a look at number 75. Identify the planetary wind belt that primarily influences the climates. So this is a reference table question, and specifically page 14 of your reference table. So we're going to go there. We need to figure out the wind belt in these two locations. Both of them are in United States, and that's helpful. So let's take a look at our reference table. Here's that reference table I'm referring to, the planetary wind belts. And as you know, the United States, primarily the continent, is right in between 30 degrees north and 60 degrees north. And so we're in this area called the southwest winds. And so the answer to this question is just simply southwest wind, planetary wind belt. And I'm just going to write southwest winds. Okay, so that's just straight up reference table, figuring out the latitude and figuring out where we are on that map. Okay, question number 76 is also a reference table question. And so we're going to go to our reference table. It's asking about ocean currents. So we need to find the ocean current page of your reference table. And that's a little bit further back in the reference table. And specifically, we're talking about page 4 of the reference table. I'll write that down, page 4. Okay, so I'm going to go to the reference table, page 4. Let me just zoom out a little bit, go to page 4. And we will see ocean currents on page 4 here. Okay, and you can see along this eastern coast of North America, we have this current called the Gulf Stream current, and that goes right past Riverhead, New York. Right over here is Riverhead, okay, and you can see that is the one that's influencing it. So let's go back to our question. It's asking about what influences the climate. That would be the Gulf Stream current. So that's questions 73 through 76. All right, questions 77 through 80 are based upon this block diagram. We have some rock layers, we have some igneous rock that's intruding and coming out on the surface at C, and we have some information regarding this block diagram. Now the questions are mostly based upon rock type, so we're going to be looking at a reference table, specifically pages 6 and 7, because we're going to be looking at rock types, as well as how rocks form. So pages 6 and 7 are the go-to with this one, okay? Now, question number 77 comes right from the rock cycle chart. We need the processes that make sedimentary rocks. So I'm gonna go right to the reference table. And if we look at the rock cycle chart, it's at the top of page 6. You'll see sedimentary rocks are right here. And the processes that make sedimentary rocks are kind of the arrows that lead to them. And so if you kind of follow the process here backwards from sedimentary rocks, you'll see compaction and cementation, deposition and burial. We have sediment formation, weathering and erosion. And essentially all you're going to do is kind of describe those processes as we go from this stage of having broken down sediments and transporting them to depositing them, burying them, compaction and cementation. Okay. Now, if you think about that, the two major ones, the ones that lead directly into it, are compaction, cementation. So I'm just going to leave it at that. I'm just going to write compaction and cementation. And you could write all of them, but it only needs two, and those are the two C words that lead to sedimentary rocks. Okay, so it's simple, compaction and cementation to get to sedimentary rock layers. Number 78. Describe one piece of evidence shown in the diagram that indicates that rock unit A is younger than rock unit B. So here's A. Here's B. Notice that this magma, this igneous rock, it was a really, really hot liquid material. It came in contact with B right here. And so you have that contact metamorphism as it indicates in the key. That couldn't happen unless B was already there. A came in later and came in contact with it. And the evidence, the big evidence is contact metamorphism. Okay, I'm going to leave it at that. I'm not going to write the long sentence there, but basically you see contact metamorphism of that layer, and therefore it had to be there first. Layer B had to be there before A came. Okay. Question number 79. 79 is an igneous rock that formed at location C. How do we know it's got crystals less than 1 millimeter in size? And the key to that is just understanding where it's forming. Igneous rocks either form underground, like A, or above ground, like C. And so C is above ground. It's a volcano. You can see the volcano right here. And all this lava is spewing out on the surface. So let's take a look at a reference table, actually, for the answer to this question. How do we know they're less than 1 millimeter in size? Well, let's go to the actual chart for igneous rocks. I'm going to just zoom out a little bit here. Notice igneous rocks are either extrusive or intrusive. Extrusive onto the surface, or volcanic, right? And if we come all the way over to the other side, we can see that the crystal size of those extrusive rocks are less than 1 millimeter in size. And so the answer to this question is just the fact that it is a volcanic rock, okay? And I'll just write that. I'll keep it simple. It is volcanic. And for that reason, the lava cools very fast. Lava cools quickly. As it's exposed to the cold air, it's going to cool down really, really fast. Okay, question number 80 is a question related to metamorphism, contact metamorphism at X and Y. So if we take a look at our diagram here, zoom up a little bit, there's X and there's Y. And you'll see that it's contact metamorphism of this layer right here, this rock right there at X, and this rock at Y. And if you don't know what those rocks are, you can always use your reference table. I'm gonna help you with this one. Rock at X is contact metamorphism of limestone, and the rock at Y is sandstone. So if I look at my reference table, specifically page 7, here's the map symbols for sandstone. You can see that kind of dots there. And here's the limestone, the bricks there. So that's how I know it's sandstone and limestone. Now I'm going to go down to my metamorphic rock chart down below, and contact metamorphism, as you can see here, contact, right, of sandstone and limestone. We're looking for contact of sandstone and limestone. So here's one, quartzite, okay? And here's another one, limestone, that would be marble. Okay, so which one's which? Well, the marble would be where the limestone is. The quartzite would be where the sandstone is located. And so if I answer this correctly, X would be, oops, I should look at the picture again. X would be the limestone, so that's marble. Oops, marble. And Y would be the quartzite. Okay, so those are your two answers to those. Now, it does say to say two different ones, and then always a possibility for contact metamorphism. If you're not sure, another option would have been to say hornfels, because hornfels is any contact metamorphic rock of any other rock, but you couldn't use that twice. You couldn't use hornfels in both places because you needed two different metamorphic rocks. So you had to at least have marble or quartzite. Okay, so that's question number 80. All right, we've made it to the last 5 questions of the test, and these are all based upon this map of Crater Lake in Oregon and some reading about that. Crater Lake was created when a volcano called Mount Mazama exploded and then blew off the top and left behind basically a crater that then later filled in with some water. And so we have this really deep lake in Oregon at the top of a mountain. Really, really pretty cool, awesome geologic place. Love to go visit that sometime. Anyway, question number 81 is a field map that you have to draw the 500 meter depth ISO line. And we're really representing the depth of the lake within Crater Lake. And so I'm just going to go to that answer booklet page. And this is the map that's given to us. You'll notice that the 0 line represents the shoreline, and we're going down in depth. And this is called a bathymetric map. Basically, it represents the water depth within the lake. And you can see the 100 line, the 200 line, 300 and 400 are all drawn there. We have to draw the 500 line. And so we're just going to try to essentially mimic what you already see. And I'm going to do this as best I can, which is a little bit hard on a screen. Find the 500s first. Like here's one right there. So I'm going to start there. And I'm going to go between all the 400s and all the 500s. And I'm just kind of mimicking what's already shown to us. We want to keep all the 500s on the inside and the 400s on the outside. So you'll notice over here, like, well, where do I go here? There's only 400s over there, and I want to keep those on the outside of my line. Here's a 500 here. Okay, and here's another 500 over here. And then I'm going in between, and I'm just kind of circling around, again, keeping all the 400s on the outside and the 500s on the inside. Coming back around to that 500, circling on down here. Okay, and again, keep those 400s out there, all the 500s. There's nothing over here to the left, so I'm just going to come back around again, and I'll meet up to where I started. And that's the basic outline of where the 500 line should go. So that's that question number 81. All right, question number 82 is a profile. We need to draw a profile of the AB line that's shown on our answer booklet. And this is a little bit tricky, obviously, for me to do on the screen. I'm going to try my best on this. You would need scrap paper, and you would need your answer booklet, and you'd need to kind of compare them. And you really need to do this one slowly. Take your time completing all the plots to complete the profile. So let's take a look at our answer booklet. I actually have it right here. You'll notice that I have the actual profile located over here. Okay, I have the profile here and I have the map side by side. So here's the AB line, and I have to draw the profile from A to B here. So what I'm going to do is I'm going to take a piece of scrap paper. I'm just going to draw a yellow rectangle on here, and I'm going to put that right on the AB line, and I'm going to mark every time a line crosses my paper. So I'm going to mark A. I'll do that first, and I'll mark B. Okay, and then I'm going to mark every other line that crosses my paper. There's one right there. Oops, let me try that again. Right there, and right there, and we already have A and B marked. And then you want to label them, okay? Like A is right on the shore of Wizard Island, so its elevation or its depth is 0. The first line here is 100. The next one's 200, and you can look up above here. You can see where those lines are up above, and you follow them around and it'll tell you what they are. Okay, this next line after that is 300 feet of elevation, or depth. Sorry about that. Okay, and then B is at the 400 line. And then I'm going to take that whole entire profile and I'm going to drag it over to where my profile is located. Now I have another one over here that's already grouped up. So I'm just going to take this and I'm going to drag this over to where I have it over here. So there's my scrap paper. Now it's placed from where I have it over here to over here. Okay, so we're going to be looking at the profile now. So I'm just going to zoom in on this section over here. Really what we're looking at is this area. Okay, now, whoops. Let me undo that. Let's just focus on that area. So I'm going to take my pencil and I'm going to mark wherever that crosses my line. And I want to make sure those are all lined up. Okay, I'm going to mark this on my profile up above. So A is at 0, so I'm going to mark a dot right there. 100 is right above that, so right there. 200 is right above that, right there. 300 right there. And then 400 right there. And then all you have to do is kind of connect them together. Smooth curved line. Bringing that all the way down so they're all connected. I didn't do that one very well, but you get the general idea. Okay, so you can obviously see that that's sloping downward. It's getting deeper as you go from A over here on the left to B over there on the right. Okay, so there's your profile from A to B. All right, question number 83 is a gradient question, and gradient is a formula that is on your reference table right on page 1. Let me show you a picture of that. Here's the equations box on page 1, and you'll see gradients right there. Change in field value over distance. So I'm just going to write that onto my test here. Change, I always abbreviate with a triangle, delta, FV over distance. And we just need to figure out some values. So I'm going to take a look first. I'm going to find out the distance first, not that it's necessary to do that first, but I'm going to do that first over here. And so if we take a look, here's our map. And what you need to do is you need to take a piece of scrap paper and you need to essentially just line it up with C and D to figure out the distance here. So I'm just going to line that up, and you can see I put 2 marks on there where C and D are located. And then I'm going to bring that down to my scale down here, and I can basically estimate what the distance is from C to D. And you can kind of see that that is 1.5 kilometers. So I'm going to write that down on my test. 1.5 kilometers is the distance. And don't forget to label everything as you go along. It'll just help you make sure that you keep those labels later. And then we have to figure out the values, the field values. What is the elevation of C and D, or the depth of C and D technically? So I'm going to take a look at my map again, and we're going to look specifically right at these 2 values. C is on the shoreline, as you can tell. And you can look at that right here. Here's C. It's right on the gray area. So that's 0 depth. And D is right on this line. If I follow this line across, you'll see that that's 400. So I have 400 and I have 0. Okay, so I'm going to write those 2 numbers down on my test. 400 minus 0, which is just 400. And so essentially all I'm going to do is I'm going to divide 400 by 1.5. So that's meters over kilometers. And if I do the math there, and don't forget, you will be able to use a calculator on your test. The answer in this case is 266.7. I'll just round it. Sorry about the decimal there, it didn't really show up. Meters per kilometer. So that's how you do gradient for question number 83. Okay. Sticking with that same idea, for number 84, we're going to take a look at a possible depth of location X in Crater Lake. So I'm going to go back to that same picture that I was just on, and we're going to find location X on this map. So if you look, here's location X. It's right in the middle of this little pocket here of all these lines. So you can see that there's a line marked 400. And then you have a line marked 200. So you basically have like a little hill coming back up again here. See how these are much deeper, 500. And this is 400, it's coming back up again. And then that's 300, and that's 200. So this is higher than 200. It's coming back up again, but there is no 100 line. So you would assume that x is somewhere between 200 right here, this circle, and 100, which is not drawn. So I'm just going to pick any value between 200 and 100 for that answer. And basically you could pick anything. I'm just going to write down the range. Do not write down the range. Actually, you know what I'll do? I'll just pick the number in between. Key thing with this one is you have to come up with one depth, right? So don't write a range of numbers. Don't write anywhere between 200 and 100. Just pick a value between 200 and 100. And that is an acceptable answer. Okay? All right, question number 85. We've made it to the very end. And of course, the last question requires a little bit of work here. So we have a chart that's actually from your reference table. This is the igneous rock chart. And what we have to do is figure out the mineral composition of line YZ. And this is going to require scrap paper. Again, you're going to need to line it up along that line and figure out some percentages. And so I'm going to do that over here. I have already done this, and I want to just show you what I did. I have a scrap paper over here. What I did was I just put my scrap paper right along the edge of line YZ. Hold on, let me move this out of the way a little bit. Okay, and you can see how I line that right up with the line. Okay, and then I marked with my pen or pencil along here every time I crossed a new mineral. So like right here, okay. I also did it right here, okay. I crossed right here at biotite, and I crossed at the bottom at amphibole. Okay, so I have three minerals in here. I have plagioclase feldspar, I have biotite, and I have amphibole. And I need to figure out how much I have of each one. So I'm just going to take my paper, my scrap paper, and I'm going to slide it on over to here. I'm putting the bottom of the plagioclase feldspar line right at 0. And the top of this is going to give us our percentage right here. And you can see these lines go by 5. So 5, 10, 15, 20, 25. So this is 55% for plagioclase feldspar. So I'm just going to write that in down here on my test, 55% plagioclase feldspar. Biotite, what you have to do is just slide this on up and bring the bottom of biotite over to 0. And you can see that this is reading somewhere around, it looks like around 15%. It might be slightly more than that. Let's just go with 15. And don't forget that you will be given a range of acceptable answers for this. If you're not exactly right on, that's okay. As long as you're within 5%, you're good. Okay? And then finally, you could figure out the last remaining percentage of amphibole if you wanted to by just subtracting the other two from 100, because you know the total has to be out of 100%. And that would mean that amphibole is going to be 30%, because if you do the math here, 55 plus 15, if you subtract that from 100, that will give you 30% amphibole, because 15 and 55 are 70. But let me just check it just to make sure that that is accurate. So I'm just going to slide my paper up, and that's not bad. So if you look at it, amphibole is falling somewhere just above 25%. And remember, we kind of skewed biotite a little bit. But yeah, about 30% amphibole with my numbers that were written there. So there you go. And again, don't forget, these numbers do not have to be perfect. As long as they're within 5%, you're good. You could have said that it's about 17% biotite and maybe more like 23%, or sorry, 27% for amphibole. Okay, so you just realize you have to use scrap paper on that one. You have to take your time because that requires a little bit of effort. Okay, so that is the entire test, ladies and gentlemen. Obviously, there's a lot of challenging questions on there, a lot of reference table questions. You just need to take your time. You have 3 hours to take a Regents exam, and do your best, okay? Hopefully this was helpful for you. And if you have any questions, don't hesitate to reach out to me.